So, okay, let's start. So remember, you have the right hand rules plus another one. Remember that I talked about if there is a torque and the torque wants to rotate the system like in this direction, that thumb here shows you the direction of the torque vector. Okay, torque is a vector. So if he wants to rotate this way, the torque is going to go that way. Okay, that will be the fourth rule. So again, first rule, if a positive charge is flowing this way, the magnetic field is going to spin around. It's curling. In vector analysis, we can define the curl of the magnetic field. It doesn't want to diverge, it doesn't want to converge, it only wants to curl. And then you have this rule here. Okay, so each time you have loops of current, right, you take your fingers, these are the loops. The thumb here will show you the north. So everything happens, it's behaving like a bar magnet. That will be the north, here will be the south, and then you have the magnetic force that will apply to current or to positive particles moving. So one way you can do it, if the positive particle is moving this way, the magnetic field is pointing that way, the force will come out of your palm. If it's a negative charge, then you can use your left hand. Okay? And then I told you that force here so this is in 3D because it's a cross product. So that force is always perpendicular to the velocity or perpendicular to the current, perpendicular to the magnetic field. Okay, so that force is a deflecting force. It cannot make it go faster or slower. It's deflecting. And it works only if you have a charge, only if the charge is moving, only if you have a component of the magnetic field perpendicular to the velocity. Okay, that's the definition of the cross product. Okay, so that's just review over and over and over and over again. And last time we stopped slide 65 because I didn't have my tablet. So it comes from your book. So I will show you two ways to do it. So first of all, it can be confusing because when you work with velocity, magnetic field, and the force, the magnetic force, okay, it's in 3D. So you have to use the right hand coordinate system. And depending on the problem, you can choose your axis in different way. So this PDF here, you will find it in Dropbox. Okay, it's going to help you for calculus, vector calculus, if you didn't take it yet. You see, it has to be this way. If X is this way, Y is that way, Z is this way. See, you have to use your three finger. X, Y, Z. Or X, Y, Z. So it's a right hand coordinate system. Okay, so here you have another examples, and depending on the problem, sometimes things happening in the X, Y plane, sometimes it's happening in the X, Z plane, so you have to choose wisely. When you cross, you see you have to go this way, so that will be clockwise. I cross J is going to give you K. K cross I is going to give you J. J cross K is going to give you I. Okay, you have this. Now, if you go in the opposite, you're going to have a minus. Okay, so these are cross products. Just a review. So you will find that in your Dropbox, in my Dropbox. Okay, let's try to do this one. You can help each other. The idea, if you have a tablet, okay, you open this slide here. Okay, you can work with this one, that one, or that one. Okay, you can open it, you can crop out and try to do this one. I'm going to do it two ways. Okay, let's move. We are behind me. Okay. So what's happening here? So beam of proton, okay, so these are positive, so it's moving. So that will be your magnetic field. So do it. Don't wait for me, okay? You need to find the right coordinate system. So you have the magnetic field, and this is along the z-axis. But the velocity of each proton lies in the xz axis. And it makes a 30 degrees with the z-axis. Okay, so let's try to... So we want yz. Okay, y and z is involved. No, xz. It's touch screen. Touch screen. Xz. Maybe I'm gonna use this one. Okay, so first, in physics, you want to start with a drawing of the situation. So, magnetic field along the z-axis. So the magnetic field is along the z-axis here. Is that right? Z-axis. So that will be the magnetic field. And then the velocity is an xz, and it makes 30 degrees with the z-axis. So that means the velocity is this way. Check if I do it right. Not sure. So this is 30 degrees. Is that right? Velocity like in the xz axis, 30 degrees with the z-axis. And B is along the z-axis. Are we good? Okay, so let's use our right hand. Can you figure this out? Where is the force now? So velocity is this way. So velocity is this way. Magnetic field is that way. So it makes an angle of 30 degrees. So where is the force? Down. Right? You have to see in 3D, right? You're an engineer. So velocity is this way, magnetic field is that way, it makes an angle, so the force is down. You want to make sure to have the right coordinate system, and then after that I will show you a different way to do it. So of course it's very important to know if it's up or down, because multiple choices. One choice will be up, one choice will be down. Okay, so the magnetic force will be down. Okay, so it's gonna be like the force will be the magnitude and minus, we call that y hat, or we can call that j hat. Agree with me? Okay, once you have done the concept, now you can do the computation. Okay, what's the definition of the cross product? So the magnetic force will be Q, and then B, and V, and then the angle between V and B. Okay, by definition, that will be the magnitude. Or you can say it's going to be Q, and then that will be V, maybe the perpendicular component of V perpendicular to B. Or you can say the perpendicular component of B along V. So that's the definition of a cross product. Okay? If there is no perpendicular component, then there is no magnetic force, right? See, the velocity here has two components. It has a perpendicular component, that's the one that make that magnetic force possible. It has a parallel component, and this one is not doing anything for the magnetic force. It's just pushing the particle in this direction. But this is the component that makes that magnetic force deflection happening. Okay, this is math. Okay, it's not even physics. Okay, so let's do that. Plug in. Just plug in. So we now we just find the magnitude, right? What did you find for the? Yes, you're right. What did you get? Yes, yes. 4.8 times 10 to the negative 14, you're right. So 1.6 times 10 to the negative 19. And then you have the velocity 3 times 10 to the 5. And then you have the magnetic field is 2. And then that will be the sine of 30 degrees. So that's in magnitude. Okay? So in magnitude, okay, so do it. Magnitude is going to be 4.8 times 10 to the negative 14 Newton. Now it's from your book. So if you have the textbook in Canvas, I think there is a video also, but it's important to understand that the cross product only works if you have a component perpendicular to the other vector. Okay, so again, velocity has two components. Only this component is making the deflection happen. If you don't have that component, there is no deflection. So the magnetic force is high maintenance force. Not only you need a charge, and the charge has to be moving, but it has to be moving with a component perpendicular to the magnetic field. Otherwise, it's boycotting. Any question? Yes. But you see here, you have the velocity here, right? So it has two components relative to B, because you are doing two vectors, right? So relative to B, one component is along B, so it's not going to do anything. One component is perpendicular. Now you could do the opposite. You could say B has two components, one along V and one perpendicular to V, and you will get the same. Okay? Are we good? So if you go to engineering, more advanced stuff, this is important to understand. This is the right-hand coordinate system. It has to follow a direction. Okay, you can learn that by heart if you are taking vector calculus. And again, it's in Dropbox. Okay, and I'm going to show you the other way, which is done by your book. Okay, so this is my way. I think it's easier this way because you visualize what's happening. But they are doing just using the definition of the cross product, right? So they're going to say, okay, F is Q V cross B. So we're going to do it the calculus way. Oh, by the way, I forgot. Once you have found that the magnitude is 4.8 times 10 to the negative 14 Newton, and you did that with your right hand, so this is minus J hat. Okay, because the multiple choices will ask you, okay, which direction? It's down. So minus J hat along the y-axis. Hmm? Yes. So if it was like electron moving, so it will be plus j hat. Okay, so that will be the final answer. So your book is using this way. So the book will say, okay, v, the velocity has the velocity here has two components, one along the x and one along the z. Okay, so I'm going to do velocity equals, it's going to be 3 times 10 to the 5, and then along the x it's going to be a sine, so it's going to be sine 30, and then it's a high I hat, and then it has a component along the z, right? Are you with me? Just a little bit of calculus. 30, and that's a z, so it's a k hat. Okay, so you can do it this way. And then b is along z, so it's going to be 2k hat. Okay, so what they do, they're going to use the definition here and this. Okay, they're going to use I cos j cos k and so forth and so on. So if you do that, so this is more calculus, right? So if you do that, F equals Q, and then you have V, right? So it's going to be 3 times 10 to the 5, and then it's going to be sine 30 I hat plus cosine 30 k hat, and you cross that with 2k hat. And then you distribute. So it means you're going to cross I hat with k hat and k hat with k hat. K hat and k hat, does it work? 0, very good, right? And then you have I hat and k hat. Okay, I hat and k hat is going to give you minus j hat. So the force will be Q 3 times 10 to the 5, and then you have a sine 30, and you have a 2, and then here you have I hat cos k hat, and that's going to be minus j hat, and you get the same thing. So this is more calculus way, but notice that if you do it this way, you don't have to do your drawing. If you do it my way, you have to draw. Okay, so if you do it my way, you use the magnitude and then you have to figure out the direction. If you do it this way, that will be the calculus way. Is that clear? But you need to know this. Okay, so I thought it was nice to connect to calculus a little bit, but you have to, you can text your textbook. Okay, it's explained in your textbook. Okay, so that's said. That's good. Okay, calculus is healthy. Okay, and then this is we did it last time, and that's how it's a cloud chamber. So that's how the positron was discovered, the anti-electron. So all those particles coming from space, neutrinos and muons, and if they are charged, if they go through a cloud chamber, okay, with a magnetic field, they will be deflected by the magnetic field. And then you can figure out the mass, and that's how they discover the mass and the charge. That's how they discover the positron, the anti-electron. And we did this one, right? Didn't we do that one? That's going to be on test number 3. Did we do it? Yes? No? Okay, so can you tell me? So imagine the magnetic field is coming towards you. Out of the screen, is green positive or negative? Is red positive or negative? So take your right hand and take a guess and see if it works. So if it's a positive particle, we don't know. Okay, we don't know which one is positive. But if it's positive particle, so the velocity is this way. The magnetic field is towards you. So the force is where? Do you all agree here? Right, the velocity is this way, magnetic field is towards you, the force is down. So the red one is the positive particle. And you see, you can also see the mass. You see, this one has more momentum, it has more mass. That's why it's going to spiral down. So it's going to make a spiral, but the curvature here is larger than this one. Okay, because it has more inertia, so it's harder to curve. So this one has more mass, this one has less mass. Okay? Okay, so that I will let you do that. This one comes from MCAT. Okay, so one thing to understand is that the electric field is not high maintenance. It just needs a charge. Whether it's moving or not moving, it will exert a force QE. So the force is always along the electric field. That force along this direction will make the particle speed up in this direction along the electric field. So if it's a positive charge, it's going to speed up this way. If it's a negative charge, it's going to speed up the other direction. But at the same time, it's moving along a straight line. So it's like a projectile motion. It's doing two things at the same time. It's accelerating along the electric field, and at the same time, it's moving, it has some momentum. It's moving forward. Projectile motion. But if you have a positive particle inside a magnetic field, it's very high maintenance. First, it has to be a charge, then it has to be moving, and then the velocity needs to have a component perpendicular to B. And in that case, the magnetic field cannot change the speed, it only changes the direction. Okay, so a magnetic force deflects. And the particle is trying to spiral around the magnetic field. It's trying to go around the magnetic field lines. It make it go around the magnetic field lines. Okay, so that's a centripetal force. That's F equals ma. You have F equals ma, but now you have a centripetal acceleration. Is that clear? Okay, I think I show you already. I show you the simulation, but here we talked about mass spectrometer. So you see you have a bunch of isotopes and they have different masses, but they have the same velocity and the same charge. They go inside the magnetic field region. So the larger mass and larger velocity, so larger momentum, okay, the curvature will be the largest. Smaller momentum, so smaller mass, smaller velocity, it's going to be sharp because it has less momentum to begin with. And then you can increase the motivation by increasing B or increase Q. Okay, and it will make R smaller. Is that clear? So you can tune the magnetic fields, you can increase the magnetic field to curve this particle here so you can hit the detector. You see how it works? It's like it's called the cyclotron motion. And I think I have like somewhere somewhere I have a video, but I don't know where. Not here. Ah, ah.
So this is an evacuated glass.
So you have two loops of current. So in between in between you're going to have a very strong magnetic field going in the screen or out of the screen. It works like a capacitor, right? When you have two plates, you have a uniform electric field. These are called um, Helmholtz coils. Now you have it somewhere here, something like this. Here, Helmholtz coils. In between, you have a uniform magnetic field. So magnetic field going in or out. And then here you're going to have a beam of electron.
Heated metal. Oh, the other guy, cyclotron, is a little metal or positive thing. Sucks the electrons up to a few hundred volts at the plate. The plate has a hole for that. Some of the electrons keep going.
So that's your beam of electrons here. It's a vacuum inside.
Yeah, but it's there, being shooting down. So you're seeing the electrons in the right. Now we know that we get uniform. These two big coil wire. So there's a large coil of wire. See what pattern the electron beam makes. So here we're turning, and you can see it starting to curve more and more. Right now, it's like most of it's right there.
So you increase the magnetic field, you increase the motivation. So the radius gets smaller.
There's direct visualization. Sort of.
Isn't that cool? So what's nice with those electromagnets is that you can control the magnetic field, right? If you have more voltages, like more voltage, you're going to increase the current. If you increase the current, you increase the magnetic field. So you can tune the magnetic field so you can collect the isotopes when you are using a mass spectrometer, right? Okay, so that's used is in something called the cyclotron. So I'll talk about that, but that was an amazing discovery in the 1930s. It was designed by Ernest Lawrence from Caltech, because until then we had linear accelerator. So we only use an electric field to make a particle go faster, and then we can smash the particle into something less, or in an atom, or in a nucleus to make it radioactive. But it takes space, right? Linear. I don't know if I have a picture. It's still used today. A linear accelerator. Okay. So the principle is very simple. Right? You have negative here, positive here. You have electron. You accelerate them with an electric field. The electron have kinetic energy. So remember, potential to kinetic energy, they're going to crash. Okay, and all that kinetic energy is going to turn into, for example, X-ray, and you use that for radiotherapy. Like, God forbid, for a tumor, for example, you can use those those X-ray. X-ray for skin tumor. I don't know what they are used for. But anyway, it's a linear accelerator. And here we have a big breakthrough. So here is the idea. You're gonna first you apply an electric field. So it's gonna speed up, and then it's going to be deflected by a magnetic field. Speed up, deflected by a magnetic field. Speed up, deflected by a magnetic field. So it doesn't take so much space, and it keeps going faster and faster and faster and faster and faster, and then you can use that as a gun. Okay, and the particle becomes like a projectile, and you can make new radioisotopes. Okay, and that's a Nobel Prize. And there is a trick. I'm going to tell you about the trick, but the trick is, so you have the magnetic field this direction. Okay, so you can check there is magnetic field, the force moving this way, magnetic field going that way. So you're gonna have a force that will deflect. The trick is that when you work out the equations, the time it takes to go around does not depend on the speed. That's the trick. So we're going to look at the equation, but the time it takes to go around does not depend on the speed. So as it's going to speed up, it's going to take the same time to go half of a circle, same time to go half of a circle. So each time the particle is here over the gap, you're going to push it with an electric field. You push, go around the circle, and you push, go around the circle, and you push, go around the circle, and you push, going around the circle. Yes, the time is always the same. So that way you can have an AC power supply with an alternating electric field that will switch back and forth. So it's like a swing that you push and you push and you push at the same frequency. So that's the trick. So it was a big breakthrough. Okay, he got the Nobel Prize for that. That was super smart to do. So anyway, let's go back to the equation here. So you use those two equations. Remember, the force is a centripetal force, and that you have this equation here, the radius. So a particle inside a magnetic field wants to curl, okay, wants to go around a circle if the magnetic field is constant. So this is the simplest case. So it's go around the magnetic field line. Okay. Now, when you work the equation, you have the slide, so I'm not going to do it. But if you shake the equation here, right, we can find the period. How do we find the period? The angular speed, okay, it's going to be the period is the distance over the velocity. So the time it takes to go around is called the period. So the time for one cycle. Time is distance over speed, so it's going to be 2 pi r over v, and that's what you get at the end. So that will be the equation for the period. When you have a motion of a particle inside the magnetic field, there is no velocity here. It's not velocity dependent. So if I ask you, is the motion depends on the velocity? It does not. Okay, it's not velocity dependent. It depends on the mass. Okay, of course, larger mass, it takes longer to go around. It depends on the magnetic field and the charge. These are the motivation. But it does not depend on the velocity. Okay, so this is called cyclotron motion. Any question? From physics 1, what we call the angular speed is just the number of cycles per second. Except the unit will be rad per second. And that will be this equation here. Okay. We can also define the frequency. The frequency will be how many cycles per second, which is 1 over t. Are you with me? Any question? Okay. So, did we do this one? Okay, so first of all, which one makes sense? So first of all, you have an electron and you have a proton. Which one has a larger mass? The proton or the electron? Proton has a larger mass. It's about 2,000 times more, right? That's why in the atomic number, we only take in account, or the mass number, it's only protons. So which one do you expect to make the larger curve? The proton. Very good. So this one, bye-bye. This one, bye-bye. Okay. Does this one make sense? Can they both go in the same direction? No, because one is positive, one is negative. So bye-bye. So this one is bye-bye too, because they go in the same direction. Bye-bye. So which one is left? B. Now you can check your right hand. Very good. You can check. So magnetic, the velocity is this way. Velocity is this way. magnetic field goes into the board, force is down. When the particle is here, you see, the force will be in this direction. Okay? So remember that for the test, right? Okay, let's do something easy. No, do I have to do it or not? No, it says quick. Okay, so do it quick and then we look at the solution. So do it quick. So what's the equation you want to use? You want to use this equation, but you can remember it. It's easy. The radius depends on the momentum. Larger momentum, harder it is to deflect. And it's inversely proportional to the motivation, which is the charge and B. Okay, so you can try that. The magnetic field of the Earth is 0.5 times 10 to the negative 4. 10 to the negative 4 is a Gauss. 10 to the negative 4 Tesla is Gauss. So anyway, it's 0.5 times 10 to the negative 4. So use the equation to find the radius. So just plug in. Okay, so momentum at the top, enter, divide by, open the parenthesis, motivation. Motivation is the charge, and times B. Okay, so that's the answer. Okay, MV, the momentum over QB for the magnetic field inside the magnetic of the Earth. So the radius is 2.3. Did you get that? If the magnetic field is that right? So this is very large. If the magnetic field is 10, which is like more than 10,000, 100,000 more, you're going to see the radius is going to be very small. So here we have micrometers. Do you agree? You just plug it in, right? Any questions? It's good? You survived? Okay, very nice application here. Lots of physics, super smart. There is a video in Canvas that explains how it works. It's called the magnetron. So the magnetron was designed during World War II by the British. And it was very highly classified, World War II, right? World War II, yes. And they made the radar. The British came up with the radar. So the radar is a device that will send microwaves, right? And they will send microwaves to ping the airplanes from Germany. When Germany was trying to invade England, they will ping them, right? And Germany didn't know about that radar, so they gave up on trying to invade England. They bombarded London, but then they gave up. They say, okay, each time we come, they show up. Maybe they are, we underestimate how many pilots are available, so they gave up. But they didn't know they had the radar. You understand? It's like an echo. You send radio wave, it's going to ping the airplane and then it's coming back. So you know how far the airplane is. And the design of that was super, super smart. And after World War II, they gave the design to the American. It took a while for American to figure it out because it's simple when you understand, but it's not that simple, right? It's super smart. And then American being American, it's all about, how can we make that, turn that into making money, and they made the microwave, and that was a big, big, big thing at the time. They were the first one to have microwave, and you see these old commercials back then. So how does it work? So first of all, in physics, you have something called resonance. So anything that oscillate like to oscillate at its natural frequency, right? It's called resonance. Like if you excite a bridge, for example, and if you excite it at the right frequency, it's going to go higher, higher, higher. It's going to break. Okay. Some people, they have resonance frequency. You talk about that topic, oh wow, they go off the roof. Okay, so that's resonance as well. Now, in electronics, in electricity, you also have resonance. To get resonance, you need a coil and you need a capacitor. If this circuit here, if you have the right frequency, right, it will oscillate back and forth, back and forth. The energy will swing back and forth between the electric field, the magnetic field. That will be called resonance. So when you have resonance, you have the best efficient way to transfer energy. Right? Tesla coil is also based on resonance. Okay, so same thing here, mechanical system, you excite your system, it's going to start to oscillate, okay, at its natural frequency. And if you try to excite it at that frequency, things can go bad. So anyway, you have the same thing when you have a coil, which is called an inductor and a capacitor. You can make the current oscillate back and forth between the capacitor and the inductor, and you don't lose that much energy. Okay, it's very efficient. So they did the same thing here with that system. So inside the microwave, somewhere you have a power supply like 4,000 volts, and you have electron. Okay, so and this is the cathode and this is the anode. Okay, so this is negative, this is positive, connected to a 4,000 volt power supply. Electron here break free because it's filament, it's very hot. They will accelerate. So you use an electric field to accelerate the electron. But at the same time, inside the magnetron, so inside the microwave, you have a very strong magnet, okay, that will produce this magnetic field. So the magnetic field will curve those electrons. And then you have some oscillation happening here inside here. So this little hole that you see here, everything happens like it behaves like a capacitor and an inductor. So those electrons, they're going to start to oscillate back and forth very efficiently. And because they oscillate, any oscillating charge will emit waves, electromagnetic waves. So they will emit microwave at a given frequency, and the frequency is 2450 hertz. Super smart design. So what's the whole idea? The whole idea is transfer energy in a very efficient way from your power supply, which is 4,000 volts, to the microwave. And you do it with resonance. Okay? It's a piece of technology, super smart. And there is a video, I think in Canvas. I'm not going to play the video here, but there is a video that shows you how it works.
In the history of the world. On the internet, it also resulted in several inventions. We will explore the physics behind the we will explore the physics behind the cavity magnetron.
Okay, so you can, it's on YouTube, so you can always watch it. See? That's how it works.
And transfer their energy.
So the electrons go from cathode to the anode and they're going to oscillate back and forth. Here you have an antenna. So anyway, the idea is that energy is transferred from the power supply to the microwave in a very efficient way, and the magnetic field here is a way to transfer energy. So just an application. You can watch the video. Okay, mass spectrometer. So how it works? So first you're going to use an electric field to accelerate the isotopes, right? Or the charged particle. And let's say you don't know the mass of that charged particle. So first you use an electric field, like we did for test 2. Okay, so potential, electric potential energy, that will be the voltage turns into kinetic energy, and then it goes inside magnetic field, and the magnetic field will deflect them, and you're gonna tune the magnetic field until this gonna hit here the detector. So first it's gonna be here, you increase the magnetic field because it's produced by an electromagnet, and then you can detect it here. And then you have that equation here. So I'm not going to do the math, but you take this equation plus that equation, you massage them, you shake them, and that's what you get. So that's a mass spectrometer. An equation. So make sure, like, if it's not in your equation sheet, you can add that. Okay, so that way if you have everything on your equation sheet, it's going to be super fast when you're going to take test number 3, and the assignment that I'm going to post, it's going to be very fast. Make sure you keep track of all your equation and the meaning of the equation. Is that clear? You can use that also, mass spectrometer, to find the relative abundance of isotopes. Like, I think this is neon. So you have neon 20, 21, 22. When you have isotopes, one of them is always the largest. So you can do that. You can use a mass spectrometer. So so the cyclotron was designed by Ernest Lawrence, and he used that design to enrich uranium. And then he used that device and he called that calutron. Calutron named after Caltech because he was working there. So it was during World War II. There was a race for the atomic bomb, and the idea is to get to the critical mass of uranium-235. So if you have uranium, most of uranium will be uranium-238, 99%, but 1% will be uranium-235. So you need to enrich uranium if you want to make a bomb. Uranium-238 doesn't work, you need uranium-235. So the idea is to use, and that was his idea, and Ernest Lawrence, right? So use uranium, strip electrons so it become charged, okay, and put this uranium like in a mass spectrometer, and which one will curve the more? The smaller mass, okay? Less inertia will be sharper, exactly. And you keep doing it until, so it's the whole story with Oppenheimer and so forth and so on. It's the Manhattan Project, until you get enough uranium-235. So they got to the critical mass before the Nazi. But there was a race, and there was a trick to get first. So now we don't use this technology. It takes a lot of energy. They had to invest a lot of money inside in the project. We don't use this technology anymore. They have different ways to do it. But at the beginning of the war, that's what they did. And then they could drop the bomb on Hiroshima. Hiroshima was atomic bomb, so uranium, using uranium. So in Iran, you hear about Iran a lot, is they enrich uranium using centrifuge. Centrifuge is same thing. Okay, you make those isotopes spin, and the small mass will have a sharper turn, and you collect them. The thing is, with uranium enrichment, as you keep enriching and enriching uranium, it gets easier and easier and easier. When you hit a threshold, that's it. It's so easy that tomorrow you can have the atomic bomb. Okay, so in the US they don't use centrifuge; they use another technology. Okay, shall we do this or not? We can do what does it say? 80. We can do number 3. Okay, let's do number 3 here. Big idea. Okay, let's do number 3. So make sure you drag all the equations that you have them in your equation sheet, okay? Because otherwise it's all over the place and you don't know what's going on anymore. So let's do number 3. So you have to remember from test number 2, right? So the electric potential energy. So this is the electric potential energy. It's going to be turning into kinetic energy. Okay, so that's one equation. Second equation, the radius for a magnetic field. So a charge particle in a magnetic field depends on the momentum. Larger momentum, harder it's to curve. And it's inversely proportional to QB because this is the motivation. And then you massage and then you malax. And when you massage and malax, you're going to get that the mass is Q R square. This is R. 2 times the voltage B square. So I have eliminated V. So you isolate V from here, from equation 2, you plug that into equation 1. Equation 1, equation 2. You plug V into here. Okay, so now you can, the goal is what? To find the mass. Positive, so it says E, so E is 1.6 times 10 to the negative 6, right? 19. That's milli. And radius 0.071 meters. Okay, so plugging in. Plugging in, plugging in. What do you get? See, so 1.6 times 10 to the negative 19. And whatever here is 2 times the voltage, 150. Radius square, so 0.071 square. And then 25 times 10 to the negative 3 square, something like this. So the mass is one point two two or 1.6? 10 to the negative 7 for sure. So I found 1.6, but maybe it's 1.2. Anyone else? Do it, don't stare. Come on, do it. More you do here, less you do at home. Like do it high. It's 1.6. Okay. So that will be the charge of what? At the mass of a. Okay. Okay. What about here? So here we have the same idea. So it's going to be accelerated, through a voltage. You apply a voltage, so it's going to accelerate, and then it's going to be deflected. Tell me if it's positive or negative, the charge. Use your right hand. So suppose it's positive. Let's see if it's going the right way. Okay, so the magnetic field is in the board, right? So the velocity is this way. The magnet, let's say it's positive. Velocity is this way. Magnetic field is in the board, so the force should be so it's not happening. So it means it's negative. Okay, so the particle is negative. Okay, and this one is the same, so it's easier. So motion. So you have something called helical motion. Helical motion. So let's see if I have a something like this. So when you have a magnetic field and a particle is coming from space, for example, it has velocity. If the velocity has two components, one that is perpendicular to the magnetic field and one which is parallel to the magnetic field, two things will happen at the same time. It's going to move forward, but at the same time, it's going to be deflected. So this is called helical motion. That's happening for the magnetic field of the Earth. Those charged particles, they circle around the magnetic field of the Earth. And because you have an acceleration, centripetal acceleration, they burp out light. Okay, so that's the Van Allen belt. I showed you last time already. I don't want to look for it. But here I have another. So a charged particle inside a magnetic field, if it has a velocity with two components. So here it has up component. Okay, so it wants to keep, it has a component along the magnetic field lines. So a component up, okay, so it's going to move up, but it also has a component perpendicular to the magnetic field, so it's going to be deflected. So it's doing two things at the same time. Okay, because you're going to have one assignment, so I have to do it. Oh, Van Halen, that's, you see, this is the Van Allen belt. So you have the magnetic field line here. Those particles here, they get trapped around the magnetic field lines. So they circle around and they move forward at the same time. They are losing energy in the form of light. Okay, so that was discovered during the Cold War by the American, maybe by someone named Van Allen. Guess, not sure. Uh, let's see. Come on, come on, come on. I am in another dimension. Ah, fine. Uh, no, that's not the one. It's not the one, it's the other one. That's phased out. They don't have that anymore. Okay. So you have the magnetic field here. So the particle here has a velocity, but the velocity has two components. One which is perpendicular to B, but one which is along B. So it's going to do two motions at the same time. It's going to make a circular motion and a forward motion. So it's going to look something like this. So it's moving forward because of the parallel component of the velocity, and it's making a circle because of the perpendicular component of the velocity, right? Because the motions are independent from each other. They mind their own business. They are doing their own thing. Uh, I'm lost again. Oh, it takes so long. Yeah, looks like this, right? So because the magnetic field is not constant here, you can have, so it's gonna accelerate, slow down, and then reverse. And why it's doing this? It's gonna emit light. Okay, and I lost my slide. Keep, have to keep cool. Let's keep cool. I'm cool. Everything is cool. Da da da. Boom boom. Okay. Okay. So again, I hope you understand that everything comes into components. We are dealing with vectors, and each component is doing a different thing. So that component here is perpendicular to B, so it's going to make the circular motion happen with the radius defined by the equation. And these components here make it move in this direction. So they mind their own business and they are doing their own thing. Okay, so it's called a helical path. And there is a very nice textbook problem that I just want to go over it a little bit because that's going to be in an assignment. So try to do it. If you go, it looks complicated, but it's not. If you do it step by step, if you do it step by step, it's not that bad. So the velocity has two components. One component along B. So that component is only involved in making the particle moving in this direction. It cannot deflect. And that component here is making the circular motion happen. So so it's like physics 1. You have a set of equations for the x motion, the motion along the x, and you have a set of equations for the circular motion. Okay. So staring doesn't help. Why don't you do it? Because I want to get over that and move to the next unit. And for those who came late, make sure to catch up. And also we have a test number 3 coming up. So don't miss test number 3. Okay, blah blah blah. So we have the magnetic field, we have y component 0, we have a z component, and we have a x component of the velocity, and the magnetic field here is along the x. And they are big nice because usually they don't draw anything, but here they did. So A, okay, find the force on the proton its acceleration. So the force is the magnetic force, right? Okay, so the magnetic force equals Q, the component perpendicular to B times B. Okay, velocity has two components. We take only the one that is perpendicular to B. Agree? Okay, so F equals Q, perpendicular is the V sub Z times B. Okay, so you can do that. The Z, where is Z? Z is here. Okay, so that will be, because it's a cross product, you want only the component perpendicular, right? So 1.6 times 10 to the negative 19, and that's 2 times 10 to the 5, and the magnetic field is somewhere 0.5, 0.5. Exactly. So times 10 to the negative 14 Newton. Did you all get that? Okay. And then it says acceleration. So the acceleration is a centripetal acceleration. Okay, so it make it go into a circle, but the definition is still F equals ma. So it's just the force divided by the mass, even though it's a centripetal acceleration. So you divide by the mass, and the mass, oh, it's a proton. Okay. Times 10 to the 12, right? Meter per second square. So don't think it make it go faster or slower. It's just centripetal acceleration. So it's changing the direction. Okay. So B, find the radius. So the radius, by definition, remember, it's the momentum divided by the motivation. Okay, so you take the mass, you may, oh, but V has to be VV, right? So it's not V, it's not the magnitude. We don't want the magnitude here. We just want the component involved into the circular motion. So you could say that R equals M perpendicular, the component perpendicular over QB. Okay, so that's gonna be do you all do it? Almost there. I lost internet. How come there is no internet? Oh, now they want me. Okay, so M is the mass. That's the perpendicular component. Divide by the charge and B. What do you get? Are you sure? Yeah, 4.2 times 10 to the negative 3, right? Yeah. So make sure that you frame the denominator. If you don't frame the denominator, it's going to multiply by b. So make sure the denominator, like you do m times m enter times v enter divided by q enter divided by b enter. Okay, so otherwise that will be millimeters, right? So 4.2 millimeters. Okay, then the angular speed of the proton. So what's the angular speed? Is cycles. It's like cycles per second, right? So it's going to be 2 pi over the period. Or you can say the period. You can say that the period, you can say that the velocity z equals 2 pi r over the period here. And or you know your equation. Now if you look at the equation, it's going to be omega is q b over m. Or you can use that. That will work also. But this is the angular speed from physics 1. It's like cycles per second. So how many cycles per second? Or rad per second. So it's just qb over m. Which is 2 pi over t. So you can find t, or you can use this equation instead. I found 1.3 times 10 to the negative 7 second. No, that will be the period. So I don't know the answer for omega. I know the answer for t. For the period? Oh, not the period. For omega, what did you get? So omega, you can use 2 pi over t. Oh, and it's going to be 4, I think it's 4.8 times 10 to the 7 rad per second. Yeah. Oh, okay. So it's good. So what did you use? You use this one? Yeah. Okay. Yeah, you can use this one. Yay. There is a new movie and they said it's really good. I don't know, Hail Mary, something like this. Hi, did you watch it? Someone watch it? No? Oh. They said it's been a long time since we didn't have such a good movie because they don't use AI to make the special effect. They use like they build like real stuff. Yes. How do you say that? Practical effect? Ah, I didn't know. I didn't know the term. Yes, that's what they did. And they don't try to be political, so that's cool. It's not a dystopia. Apparently, it's very funny. So anyway, the pitch. So what do we call the pitch? The pitch is this. This is the pitch here, delta x. So because we are looking for delta x, so it's like physics 1, we're gonna focus only on the x-axis, right? It's doing its own business. So it's moving in this direction and the velocity is v sub x. So during the time t, okay, so the t is the period. So it goes around, and it comes back here. From top to top. From the top, bam, 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 come back to the top. So that will be the period. During that time, it's moving forward by delta x. So it's like physics 1. So delta x equals the velocity times the time. But the velocity here is only the x component. Okay, so the pitch will be the x component, which is 1.5 times 10 to the 5 times the period, which is 1.3 times 10 to the negative 7. Agree? So motions are happening independent from each other. They do their own thing. Okay, and again, the period is the time to go from top, boom, 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 back to the top. So if you have a view, if you look this way, okay, you're gonna see just a circular motion. So it's a projection, right? That time here is the period. So anyway, and you get 0.0197 meters. Did you get that? I got 0.0195. 5? Okay, let's put a 5. So 1, 2, 3. So 19.5 millimeters. Okay? So it's in the textbook. So you and textbook, they always have like a extension, right? The comment, and it's very nice. It's a very nice textbook. Okay, any question? So if you go step by step, it's not that challenging. Okay, so Van Allen belt during the race, Cold War, space race, okay? You see, because each time there is an acceleration for a particle, there will be emission, right? It's gonna radiate. There will be radiation. So it's those beautiful display of colors. Okay, you can use this idea to make a plasma bottle. So it's a way to keep plasma. Okay, so you have a plasma, so it means the electrons have been stripped off. Like let's say you have hydrogen, for example, and you can keep them here thanks to that magnetic field. So the application will be, for example, tokamak. Okay, so you keep the plasma here trapped inside, and then you can use that to have fusion happening. Okay, so it's a way to keep the plasma confined here. Okay, and then we have what it's called a velocity selector. So in a mass spectrometer, when you want to find the mass of isotopes, you want to make sure they have all the same velocity. So you have to use what it's called the velocity selector. So you can take your hand and you are using two fields, the electric field and the magnetic field. Okay, so typical question for a pop quiz, maybe for test number 3, I forgot. But you see, if the velocity is coming there and it's positive, so velocity is coming there, it's positive, the magnetic field is inside the board. Do you all agree the magnetic field the magnetic force will be to the left? Yeah? Velocity up, magnetic field in, force is to the left. Do you all agree? So it should be here. This one is the magnetic field, right? Doom, doom, doom. Yes, magnetic field here. The electric field force, the electric force is along the electric field. Okay, and then you're gonna tune the magnetic field until those two forces cancel each other. So you can select the velocity that you want. Okay, so it's a velocity selector. And there will be I don't know if the pop quiz is about that or not, but you see you have the force QVB is the magnetic force equals the electric force here, cancel out. Okay, so V equals E over B. It's easy to tune the magnetic field, so you can change the magnetic field until the beam here goes along a straight line. Okay, so that way you make sure that all the isotopes will have the same velocity. I'm going to